So, next we have got this loads instruction. So, you want to load some byte which is pointed to by this source index register and load that into the accumulator register, and that for that purpose we have got this loads B. So, loads B instruction, what is it doing is that this DS into 16 plus SI. So, that memory address location, so it will be copied into AL register, and then if DF is 0, then SI value will be incremented, if DF is 1, then SI value is decremented. So, if this loads B is having that REP prefix, the repeat prefix, then this operation will be carried on till the Cx becomes equal to 0. Okay. So, that way we have got this repeat this REP prefix useful for doing that for scanning through a list of characters, a string of characters, or loading string of characters one after the other into the accumulator and doing some operation there. Similarly, we have got this loads W. So, here also it is doing the same operation, where it is loading into the AX register the memory location content pointed to by MA and MA plus 1. Then just opposite of loads we have got STOS, store string. So, store string again it is byte or word. So, this is so memory address is calculated as ES into 16 plus DI. So, store STOS. So, this uses the destination index register or DI register, because now we are going to store. So, that is the destination. So, it is taken as ES colon DI. So, that is the ES colon DI will be the destination address, and that will be used. So, this STOS B, it will be copying the content of the register AL onto this memory address MAE, and if again the same thing, if DF is 0, then DI is incremented, if DF is 1, DI is decremented, and we have got STOS W, where this word will be stored, the AX will be stored in 2 successive bytes at MAE and MAE plus 1. So, that way we can have this destinations this store operation carried out. So, there are next category of instructions that we have. So, they are called processor control instructions, like STC set carry. So, it will set the carry flag CF to 1. Then CLC or clear carry will set will clear the carry flag. Then CMC or say it will be CMC will be complement the carry. So, whatever be the complemented value of carry CF complemented, so that will come to CF. Then set direction flag. So, DF is a bit in the into the PSW register. So, for string operations we need to set it and reset it. So, this STD it will set the direction flag to 1, and clear D it will reset the direction flag to 0. Similarly, for the interrupts we can have STI for enabling the interrupts, and we have got CLI for clearing the interrupts. Then there is NOP, which is no operation, then halt. So, it is halt after interrupt is set. So, after some time the interrupt will come and it will raise the processor back to the normal operation, but this halt instruction is there. Then there is a wait instruction. So, this is wait for test pin to be active. So, this is useful when you have got a number of masters in the system. So, you have so the processor executes an wait instruction, and in the wait instruction it waits till some outside device or outside master sends a signal to the test pin, and this test pin when it is when the signal comes, then the processor will know that this now it is my time to continue. So, it will continue with its previous instruction whatever it was doing. So, this wait instruction is used for waiting for the test pin to be active. Then we have got this escape opcode memory registers type of instruction. So, instructions they are for prefixed by this escape. So, this is for passing the instruction to a coprocessor. So, 8086 has got the feature that it can support coprocessor for some operations, and those if that coprocessor instruction they are opcodes if you have. So, 8086 will not be able to understand that. So, if it finds that there is the escape bit set, okay, then the opcode has got an escape part, then it will understand that it is for the coprocessor. So, it will just pass the instruction to the coprocessor, and there is a lock instruction, it will lock the bus during next instruction. So, these control transfer instructions, so they are used for transferring control between to a specific destination or target instruction. So, basically the jump type of instruction, from one location you want to jump to another location, or call type of instruction you want to call a sub program. So, that way, so it is this the destination can be a jump or a call instructions target, or it is these control transfer instructions, they do not affect the flags. Okay. So, because they are not doing any arithmetic operation, so they do not affect flag. So, the control transfer instructions in 8086. So, there is call instruction, call can be register, memory or displacement 16. So, it will be calling a subroutine. So, this call register, so the call register, the register will have the offset from the code segment register at which this subroutine is loaded, and it will be going to that particular address. So, similarly, the call memory. So, this call memory, so memory will have the offset, and then with respect to the CS, that memory will be added and it will be jumping to that particular address. We have displacement 16, the immediate value, immediate displacement can be specified, and that can be executed in the, that can be taken as the destination address for call. Similarly, we have got jump instruction, register, memory, displacement 8 and displacement 16. So, you see that there is this displacement 8. So, this is for this relative jump, and rest of the thing they are the normal jump instructions, and then there is a return instruction to return from the subroutine. So, this conditional branch instructions of 8085. So, they can this branch instruction, there are some conditional branch instruction. So, they will check that the conditional branch instruction can be signed or they can be unsigned. Now, this they will check flags, and if the condition is true, then the program control will be transferred to the new memory location in the same segment by modifying the content of the IP. So, the IP register content is updated, so that it jumps to the next address. So, if you try to differentiate between the two, so it is like this, that in these instructions which use conditional branch instructions. So, we have got this JE, jump on jump if equal, then jump on not equal, jump on greater or equal, jump on less than, jump on less or equal. Or so similarly, we can have this JE is we can have JZ also. The JE and JZ, they are same, because this is checking for equality. So, it will check the 0 flag. So, ZZ will also check the 0 flag. Similarly, JNE and JNZ, they are similar. So, that way there are redundancy in the instruction set, but they can be useful. So, the one programmer may like one class of mnemonics that can be done. On the other hand, for this conditional unsigned conditional branch instructions, so we have got some of the instructions are different, like say this jump on less. So, we have got jump if below, JB. So, similarly jump if not above or equal. So, they are same as this JB. So, there are so they are the unsigned things. So, they do not check the sign bit, whereas they actually check the sign bit. So, both of them otherwise they are same. Now, so these are the instructions that will conditional branch instruction that affect the flags, and these the flags that are affected. So, jump on carry. So, this if the carry flag is set, then it will go. So, so then it is for JNC will check the carry flag to be non-zero. So, that way this individual status bits will be checked and the corresponding jump will take place. So, if you just try to compare between this IO port mapping, IO port access, then they can be, there are two types of accesses. One is that memory mapped IO, another is IO mapped IO. So, in case of memory mapped IO, the IO port locations, so they are accessed as memory locations only. So, the memory address that we have, so 20 bit address, that 20 bit address is used for access the IO device also. The memory, the address decoder, it will have some selection line. So, that will be fed to this IO device. So, that those devices will get selected when a particular when the desired address is desired 20 bit address is put onto the address bus. The IO port or peripherals can be treated like memory locations, and all instructions related to memory can be used for data transfer between IO device and processor. So, this is the memory mapped IO operation. So, IO ports are treated as memory locations. data can be moved from any register to ports and vice versa, just like you can move between the memory location and register. So, here also you can use all those instructions. So, as a result your the movement of data becomes easier. And when memory mapping is used for I/O devices, so full memory address space cannot be used for addressing memory. So, that is obvious, because some of the locations we are reserving for I/O device access. So, we cannot use all the memory locations accessible to the program. So, it is useful only for small systems where memory requirement is less. So, if you are not using full 1 megabyte of memory space, then in your system, then possibly you can also put that I/O device as part of this memory, and so that you do not have to have separate decoder for the I/O access. So, the processor will execute memory read and write operations for accessing the I/O device, and this M by I/O bar pin. So, this is asserted high because all accesses are memory access. So, even if you are doing an I/O access, so this is basically a memory operation. So, this is this M by I/O bar pin. So, it is set high. On the other hand, we have got this I/O mapped I/O type of operation, where we have seen that I/O port addressing 8 bit or 16 bit. So, 8 bit is direct operation, direct addressing, and 16 bit is register indirect addressing via some register. And this the only instructions that we can use in I/O mapped I/O feature is in and out. So, unlike that move type of instructions, unrestricted move type of instructions between register and memory locations. So, here it is restricted to instructions like in and out for doing data transfer between I/O device and the processor. So, data transfer takes place only between accumulator and ports. So, it cannot be used to transfer between any set of registers, whereas in case of memory mapped I/O, so you can have data transfer between register and any register and the I/O port. Full memory space can be used for addressing memory, because now the memory space is not restricted by these I/O devices. So, you do not have to reserve memory locations for I/O. So, it is so this full memory space can go for I/O. It is suitable for systems that require large memory capacity. So, if you have got large memory capacity, then that maybe full 1 megabyte is used for addressing for putting memory into the system. So, in that case, for I/O devices, so we have to have separate I/O mapped I/O. And for accessing these I/O mapped devices, the processor executes I/O read or write cycle. So, we have got this as the execution is like instead of memory read write cycle, it is I/O read write cycle, and those status bits like S0, S1, S2, S3, those status flags that we have. So, those status flags will indicate that it is doing a different type of access, and this I/O M bar line. So, M by I/O bar line. So, that is asserted low. So, that is so it is low means it will be it means that it is accessing some memory location. So, that way this M by I/O bar pin, so that is made low, and that is so this is the basic difference between memory mapped and I/O mapped I/O. So, you see the major point to note is the memory capacity is an issue. The second important thing is the instructions that you can use, like in and out here and all memory movements here. That is the second thing. Thirdly, the extra hardware that is needed for decoding this I/O addresses that is required for I/O mapped I/O and not required for the memory mapped I/O. So, otherwise they are same. So, depending upon the application that we have, so we have to choose between these two mappings. So, another interesting thing that has happened with 8086 is that 8086 when it came to the market. So, previously there was 8085. So, 8085 interface, it has got 16 bit address data bus. Okay. So, this data bus was also multiplex. So, altogether it was a 16 bit interface. So, all the on a board, so on a PCB, so the processor was occupying some pin locations, and the bus was only 16 bit. But now, if you just take out that 8085 chip and put the 8086 chip, it becomes incompatible hardware wise, because now you have got say 20 bit bus. Okay. So, that makes it difficult. So, what this Intel people did is that they came up with another processor 8088 internally, which is similar to 8086, but externally the interfaces are modified. So, we will look into this 8086 and 8088 comparison. The execution unit is similar, instruction set are similar, but the bus interface unit part there is difference, there are differences. So, in case of 8086 we have got 16-bit data bus lines obtained by demultiplexing AD0 to AD15. In case of 8088 we have got 8-bit data bus line obtained by demultiplexing AD0 through AD7. In 8086 we have got 20-bit address bus. So, here this is this will be 16-bit, this is not 8-bit. So, this is a 16-bit this is a 16-bit address bus. So, we have got this 2 banks of memory, each of 512 kilobyte. So, here it is a single bank of memory. Then this is 6-bit instruction queue, 6 byte instruction queue, but here it is 4 byte instruction queue. So, these are not bits. So, these are bytes. So, this is 4 byte instruction queue and here it is 6 byte instruction queue. And clock speed that you can have in 8086 are 5, 8 and 10 megahertz, but here it is 5 or 8 megahertz. Now, in minimum mode of operation, so pin 28 is assigned the signal M by IO bar, and in case of 8088 pin 28 is assigned the signal IO by M bar, because this was a variation. In 8085 the signal was called IO by M bar, in 8086 so it is M by IO bar. So, that modification is reverted, so that it is IO by M bar in 8088. So, to access higher order byte, in case of 8086 BHE bar signal was used, but in 8088 that is not required, because the data width is only 1 byte. So, this BHE bar signal is not there. So, next we look, otherwise the internal operation everything is same. Next thing that we look into is the coprocessor 8087. So, 8086 it can operate in along with other masters, and as you have seen that in the instruction set of 8086 there is a provision by which you can tell that these instructions are for the coprocessors. So, you can say that the instruction are escape sequence instruction, and if the 8086 processor finds that it is an escape type of instruction, so it will pass that instruction to the coprocessor. So, 8087 is one of the coprocessors that you have that is very widely used with 8086. So, this is basically a coprocessor for doing complex mathematical operations. So, 8086 you see that it can do basic arithmetic, arithmetic and logic instructions, but it cannot have floating point operations and all that. So, those can be done by this coprocessor. So, a multiprocessor system that comprises of 2 or more processors. So, and entire task is divided into subtasks and they are distributed to different processors. So, advantage, better system throughput, instead of having a single processor, now we have got more than one processor. So, that way we have got the advantage that it is giving us more computational power. Each processor will have its local bus to access local memory or IO devices, so that greater degree of parallel processing can be achieved. So, there is a local memory, and the processor will have a local memory and local IO ports, in which it will be accessing the locations, memory locations and IO ports locally. But and whenever it needs to access some global memory location, so there has to be some synchronization between the processors. So, system structure becomes more flexible. So, one can easily add or move modules to change the system configuration without affecting other modules in the system. So, you can have more number of processors attached to the system in a multiprocessor system without affecting the others, and so that is the essence of this distributed processing. So, in case of 8087, so this is specifically designed to take care of the mathematical calculations involving integer and floating point data. So, that way it relieves the processor, the 8086 processor, for doing complex operations, okay, and those can be taken care of by 8087. So, they are also 8087 is also called math coprocessor or numeric data coprocessor, numeric data processor or NDP. So, that way we can have a number of mathematical operations done by 8087, while 8086 is doing some other operation in terms of internal computations, so other instructions. So, you have to put 8086 in the maximum mode, and then you can connect this 8087 with the 8086 through that request grant lines and all that. So, if you look into the features of 8087, so it can operate on data of type integer, decimal and real types with lengths ranging from 2 to 10 bytes. So, you see up to 10 bytes means, so the huge numbers can be handled by this. 10 bytes means it can handle 80 bit number. So, 80 bit number is really a huge number. So, instruction set of 8087, it has got the square root, exponential, tangent function. So, in addition to normal addition, subtraction, multiplication, division, so you can also compute square root of a number exponential, and these numbers can be 10 bytes long also, as we have seen in the previous point. The numbers can be 10 byte long also, and you can easily compute the all these things like square root, exponential, tangent of some value. So, that way and the other operations are definitely there, like addition, subtraction, multiplication, division. So, they are very much there. High performance numeric data processor. So, it can multiply two 64 bit real numbers in about 27 microsecond and calculate square root in about 36 microsecond. So, that is a big thing, because two 64 bit real numbers, if it can multiply in 27 microsecond. In case of 8086, multiplication operation, the division operation particularly, so it takes about 80 cycles for normal 16 bit numbers. So, here it is in 27 microseconds. So, it will finish off this for this 64 bit real numbers. So, that is a huge improvement, and the square root can also be obtained in 36 microseconds. So, this way many of the mathematical calculations we can put it onto the 8087 for relieving the 8086 processor for doing those. And if you want to do them using 8086, means you have to write programs for doing that. So, it will be software driven module. So, that way it will take more time. Okay. And it follows IEEE floating point standard. So, there is a standard given by IEEE. So, it is following that standard, so that any other party or any other processor who follows this IEEE standardized floating point standard can use this 8087 as the coprocessor. It is a multi-bus compatible. So, it is compatible with this 8086 bus structure. So, so next if you look into this pin diagram, so it has got this AD0 to AD7. So, out of this AD, so this is AD0 to AD15, and this address 16 to address 19. So, this is exactly same as 8086 this address bus structure multiplexed with the data bus and this status lines. So, 16 bit 16 multiplexed address data pins and 4 multiplexed address status pins. So, that are there. So, it can have 16 bit external data bus and 20 bit external address bus, just like 8086. So, that way it is going to be useful. Then the processor clock ready and reset signals are applied as clock ready and reset signal for coprocessor. So, this clock reset and ready, so they are coming for the from the 8086 processor, and they are connected to this 87 also. So, if there is a global reset, then this reset pin will be affecting 8087 also. So, it will be this will reset the 8087 processor also. Then this request grant line, so they are useful for getting the control of this address and data bus from 8086, and then interrupt line is there, by which it can tell the processor 8086 that okay, I am done, you can continue now, like this over this request and grant lines. So, it can be done. So, there is a busy signal. So, busy signal from 8087 is connected to the test bar input of 8086. So, why? Because if the 8086 needs some result to be computed by 8087 before it can execute the next instruction, then the user can tell 8086 with a wait instruction and keep looking for the test bar pin until it finds the pin low. So, this this wait instruction we have seen previously. So, it checks for the test bar pin. So, suppose we have got a complex computation and the user finds that it needs the value of x to be computed first, but this value of x can only be computed by this 8087. It may be say square root of some value, say square root of y or something like that. So, it requires 8087. So, what the processor, what the user will do in its program. So, it will put this wait instruction, and before that it will put this sqrt instruction for this y and put an escape before that, to tell that this is basically an instruction to be executed by the coprocessor. Now, it puts this wait instruction, that means that the program or the 8086 processor will now wait till this test bar line becomes active. Okay. So, this is so when this busy signal is becoming low, that means 8087 has finished completing doing the square root computation. So, possibly the user program can continue with the next instruction. So, that can be, that is the purpose. So, a low on the busy output indicates that the 8087 has completed the computation. So, the 8086 can continue now. Then for this request and grant lines, so this RQ GT0 and RQ GT1. So, this request grant lines, so this the request and grant lines of 8087 are connected to the request grant lines of pins of 8086. So, you can have a number of such devices, number of such I should say number of masters, and so the 8086 provides 2 such request grant lines. So, that way you can in 8087 also we have got 2 such request grant lines. So, this line is used to request the processor 8086 to release the address and data bus lines. So, once they are released, then this request is granted. So, then this GT line, the GT line, the grant signal will come, and then the processor will be accessing this address and data bus without any problem. So, it will know that the 8086 has released that address and data bus lines. So, it will be able to proceed with that. So, since there can be multiple such devices connected to 8086, two such devices can be connected on line 0 and line 1. So, here also the same thing, it is the 2 lines, 2 devices can be connected on these lines. Then the interrupt pin. So, interrupt pin is connected to the interrupt management logic. So, 8087 can interrupt the 8086 through this interrupt management logic at the time error condition exists. So, if there is some error condition, so during the execution some error has occurred, maybe it is a divide by 0 or something like that, then it can send an interrupt to the 8086 telling that there was an error in the last computation. So, that way this interrupt line can be activated and the 8086 can be informed that there is some error in the last computation. Then the status lines is S0 bar, S1 bar, S2 bar. So, this is going like this, that if it is 100, so this is not used, then 101, so this is read memory, 110 write memory, and 111 it is passive. So, these settings are more or less similar to what we have in 8086 also, the similar lines were there, and the interesting thing is only for 111 where the processor is not doing anything. Okay. So, that is it is passive mode, and 100, 101. So, they are so 100 is also that is not used. Okay. So, this is that is left by the designers for some other purpose, that is not documented, and this 101 and 110 they are for read and write memory operations. Then we have got this QS0 and QS1 lines. So, QS0, QS1 lines. So, if it is 11, then the subsequent byte of opcode will be taken from the queue. If it is 10, then the queue is empty. 01. So, these are same as that 8086 also. Whatever we have got in 8086. So, similarly, we have got this QS0 and QS1 bits controlling the showing the status of the instruction queue that we have. So, those values are coming to 8087 processor. So, the 8087 will know that this is the status. So, based on that it will try to fetch the next instruction from the queue, or if the queue is empty, it will not do anything, it will raise the busy signal telling that it is over, it will make the busy signal low telling that the instruction is over. So, this overall connection is like this. So, this 8087 instructions are inserted in the 8086 program. So, this is the first thing. Now, 8086 and 8087 reads instruction bytes and put them in the respective queues. So, 8086 and 8087 they have got separate instruction, the instruction queue. So, the instruction comes to both of them and then they are put onto the queue. Then one cycle is no operation, then 8087 instructions they have 11011 as the MSB of their first code byte. So, this is the thing, the opcode part. So, 11011 this is that escape prefix that I was talking about. Then this when this escape prefix is seen, so 8086 will understand that this is not for me to execute, it is for 8087. So, 8086 will skip over that instruction and 8087 will take that instruction for execution. So, 8087 keeps track for this ESC instruction by monitoring this S2 bar to S0 bar pin and AD0 to AD15 of 8086. It also keeps track of this QS0 to QS1. So, Q status being 00 it will do nothing, Q status is 01, then 8087 compares the 5 MSB bits 11011. 01 means there is some byte in the memory location in the queue. So, it will compare the 5 MS most significant bits with 11011. If there is a match, that means it is an escape instruction. So, the instruction is fetched and executed by 8087. If there is an error during execution, then it will send an interrupt to the 8087 will send an interrupt. If there is a error during decoding this ASC, the escape instruction, so it will send an interrupt. Otherwise, it will do a normal memory read write, additional words may be required. For that this RQ GT0 those lines will be activated, by which it will access the memory for getting additional operands, and 8087 busy pin is high. So, that pin is connected to this busy pin is connected to the test bar pin. So, this test bar pin is not active now. So, after some time when 8087 will be finishing the operation, then this busy signal will go low. The 8086 processor may be executing an wait instruction for this time, because as I said that if the instruction value that is computing is useful for 8086 in the next instruction, then it will be waiting with an wait instruction, and when this test bar pin goes low, that means the instruction was over, execution was over, and then it was then it will be the 8087 has written the value onto the memory location and 8086 can take that value. So, this coprocessor, so if you just compare their operations, so 8086 86 or 88, so if it finds an escape sequenced instruction, so it will wake up the coprocessor. So, it will monitor this 8086 or 8088, and then if it is not an escape, then it will 8086 will be executing the instruction, then it will go into the wait state if there is a wait instruction is there. On the other hand, if it is an escape sequenced instruction, the coprocessor which was monitoring the 8086 or 88, so it will be triggered that it will find that there is an escape instruction. It will deactivate the host's test pin and execute the specific operation. So, here the operation will be executed. Of course, it will take help of that request grant lines to get access to the memory locations where the operands will be there. Then once the instruction is over, instruction execution is over, it will deactivate that busy line and thus activate the test pin for the 8086 processor. So, it will wake up the processor and then it will continue, and this coprocessor goes back to monitor this 808688 again. So, this way this coprocessor can be interfaced with 8086 and they work in an integrated fashion, so that many of the operations are done by the coprocessor and 8086 is relieved of those operations.